Welcome everyone. I'm re-recording the 12th session because in the last time uh, our video was not recorded properly. So this was week 12 discussion. I will basically discuss the same slide which I already prepared. So let us start. Normal operator spectral theorem and forms. This was these were the topics of the week 12. Okay. So here are some results which you can already see and find them in video in class lecture also. On a finite dimensional inner product space, every self-adjoint operator has a characteristic value and characteristic vector in fact. Okay, finite dimensional inner product space. It is necessary for for infinite dimensional space. A self-adjoint operator might not have a characteristic vector. A counterexample was given in classroom. Okay, for that you can see lecture. Okay, so next result was if W is a subspace of V and V is finite dimensional inner product space, and let T be linear operator on V and W be T invariant subspace, then W orthogonal complement is invariant under T star. This is also very easy proof. For this you can see class notes, or I don't want to do this right now. Okay. See class notes if necessary. TP is self-adjoint operator on V, then there is an orthonormal basis for which works as means each of basis vector is eigenvector of T. It in fact implies that T is diagonalizable, right? For diagonality, in fact we need a basis of eigenvectors only, but here we have extra property that it is orthonormal basis. Okay. So as a corollary it can be something like if T is real symmetric, it will imply that T is self-adjoint and self-adjoint implies T is diagonalizable using this result. Okay. T is normal operator on V. Next result, T is normal operator on V, then alpha is an eigenvector associated to eigenvalue C. This is also let. Then alpha is also eigenvector of T star but associated to eigenvalue C bar. Okay, so this is also done in the class. So these all results I have mentioned here. You can see class. These theorems and the statements are basically taken from the class notes only. Matrix representation of T with respect to a ordered basis B is diagonal if and only if T is normal. Okay, if T is diagonal, then T is normal, right? Because diagonal matrices basically commutes. So T star will also be diagonal, T is also diagonal, they will commute. On the other hand, if T is normal, here comes the theorem, okay, that if T is normal, T, there is a basis for which matrix representation of T will be upper triangular, and another result was if T is upper triangular matrix, it is normal if and only if it is diagonal. So using all these results, this is done, that matrix representation of T is diagonal or T is diagonalizable if and only if T is normal. Oh, there is this orthogonal, this is necessary, we cannot forget it. If matrix representation of T is diagonal with respect to orthogonal basis or orthonormal basis, then only we can say it is normal, if and only if it is diagonal. Okay, let's see next. Here it is a spectral theorem. If T is normal operator on V and V is finite dimensional inner product space over C, C1, C2, Ck be distinct eigenvalues of T, Wj corresponding eigenspace, and Ej be orthogonal projection on Wj, then V can be written as direct sum of Wi's, and T can be written as sum of linear sum of these projection maps. Okay, so here is next lemma. A, B, M cross N matrix defined over C. There are unitary matrices U and V of order M and N, such that A can be written as U into D into V star, where D is a diagonal matrix. Not actually diagonal matrix, it is diagonal in M cross M. It is rectangular matrix. In fact, it can be of this form. It is diagonal here and 0 here everywhere. Okay, or this can be like diagonal here, 0 this side everywhere. So so what these zeros, where these zeros will be, how much they will be, it will decided by if M is less than N or M is bigger than N. Okay, if M is less than N, then this type will work. Okay, if M is bigger than 1, this type of D will work. So these rows are basically M minus N row. Okay, M minus N rows, extra rows with zeros. And here these columns, they are basically N minus M columns. Okay, so next we have this sesquilinear forms, definition of sesquilinear form: linear in first coordinate and conjugate linear in second coordinate. Here is the definition, so we'll use it. Next we have this theorem that if V is real or complex finite dimensional inner product space and if P form on V, then there exists unique linear operator T on V corresponding to F, such that F can be written as like F of alpha beta is equal to T alpha inner product with beta. Okay, this basically gives you one-to-one correspondence between uh, forms on V and linear operator on. Okay, matrix representation of forms given in the form F on V. Matrix representation of F is given by Aij, where Aij is defined as F of alpha I, alpha j, where alpha I and alpha j are coming from a basis, ordered basis, any ordered basis. Okay, so let's see. Now coming to the questions, which of the following statements are correct or is correct? So every self-adjoint linear operator on T defined on inner product space on an inner product space has an eigenvector. We need finite dimensional here. To be true, it is finite dimensional is necessary. So this statement is incorrect. So as a option, it is correct. For a finite dimensional inner product space, the self-adjoint operator T will have orthonormal basis as eigenvectors. This statement is true. We discussed it above. So this is true. That is why this option is incorrect. Every self-adjoint linear operator on T defined on finite dimensional inner product space is diagonalizable. Self-adjoint linear operator, they are diagonalizable, yes. So this option is correct because we are choosing incorrect statements. As a statement, it is correct. Every Hermitian matrix is orthogonally equivalent to diagonal matrix. Not every Hermitian matrix is real matrix, yes, because complex matrices are unitary equivalent to diagonal matrix, complex Hermitian matrix. So for being orthogonally equivalent, it should be a real matrix, then only unitary itself will become orthogonal matrix. Okay, for real matrices we have this relation. So this is incorrect. Here it should be unitary, and we are choosing incorrect statement, that is why it is correct. Let's see second question. Which of the following statements are correct for finite dimensional inner product space V? T is defined on V is normal if and only if T has such a factorization T1 plus I T2 T1 T2 are self-adjoint linear operators which commute. Okay. One part we shown here that T star is equal to T star T. We want to prove this, and we are assuming such factorization exists. Okay, so here it is T star, sorry T, and this is T star. Now because star is linear, it will go inside, and conjugate of I will become minus I, that is why it is minus I here. Now because T1 star is T1, T2 star is just T2, they are self-adjoint as by hypothesis. So now multiply them. So because T1 T2 commute, these two will cancel out. And this is also equal to this one, because it is this product will come as T1 square plus T2 square, and something which will cancel out similarly like this. Okay, so this is T star T. So now we have shown that T is self-adjoint, sorry T is normal. Now that T is normal, we have to give such a factorization, like such a decomposition maybe. How to show this, because this was not working, so let me rewrite it. For example, t is given, t is normal given. So write t1 is equal to t plus t star by 2 and t2 is equal to t minus t star by 2I. Right now this implies that t can be written as t1 plus I t2, right? To check self adjoint, t1 star is equal to t plus t star by 2 star goes inside, it becomes t star plus t star star by 2, but t star is just t, so t star plus t by 2, and this is nothing but t1 only, so t1 star is t1. What about t2 star? t minus t star by 2I star. What are we getting? T star minus t star star, but conjugate of I will become 2I minus 2I, sorry. So this is nothing but t star minus t by minus 2I minus take in numerator minus 1, or product by minus 1 in numerator and denominator as well. Then this will become t minus t star and this become 2I, and this is nothing but t2 only. So t1 and t2 are self adjoint. To check commutativity, let's see, t1 t2 is equal to t2 t1. So we have t1 t2 is equal to t plus t star by 2 t minus t star by 2I. Take 1 upon 4I common so that we can calculate what is inside. t1 square minus t star square plus t star t minus t star. But because t is normal, right? So these two will cancel out because one is in plus and other is minus. What about t2 t1? You check it, this will come out same thing, 1 upon 4I t1 square minus t star square minus or minus t star t plus t star. But again these two will cancel out because t is normal. So we have these two equal, so t1 and t2 commutes. So this was left in first time, but this time I have done this. So we have all conditions, so first option is correct. We have to choose correct statement, so first option is correct. What about product of two normal operator is again normal? No. We can give counter example, but here is a little explanation that all possible tricks is not working here. So that is, this is not a good proof, but we can give a counter example for this. Okay, so I'm not doing this again. What about part C? there exists a non-zero normal operator which is nilpotent. Non-zero normal operator will become uh, spectral theorem will imply that it is diagonalizable and non-zero. Non-zero means some non-zero entry in the diagonal. So once it is non-zero in a diagonal entry, any its power will become non-zero only. So it cannot be nilpotent. So this is incorrect statement. Every complex symmetric matrix is self-adjoint. No. Here is an explanation. Counter example basically. This is symmetric, but while conjugating A star, it will become minus I in anti-diagonal. So A and A star, they are not equal. So A cannot be self-adjoint. Here it A is not self-adjoint, but in general is also need not be self-adjoint. Okay. It can be self-adjoint if all entries are basically real, but it is a complex matrix. So this statement is wrong. Okay, so let's see next question. Consider a matrix 1i I1 orthogonal basis for V consisting of eigenvector of T is. First I calculated it characteristic polynomial for A like this. This calculation shows that characteristic polynomial is this lambda square minus 2 lambda plus 2, and which gives eigenvalues 1 plus I 1 minus I. For lambda is equal to 1 plus I, we have eigenvector x1 1 1. Okay. For lambda is equal to 1 minus I, we have eigenvector 1 minus 1. So these eigenvectors are basically linearly independent because lambda and lambda 2 are distinct. So this becomes a basis, but this is not orthonormal. It is orthogonal also. You can check it. This is orthogonal basis in fact, because our matrix was symmetric. So we got somehow okay. Anyway we got we got orthogonal basis consisting of x1 and x2. Okay, but here because options were not according to us, so we have to normalize our basis vectors. So in x1 I just divided by norm x1, so this was 1 1 by norm x1. Norm x1 was 1 by root 2, and in x2 1 minus 1 I divided norm of x2, that was also 1 by root 2. Sorry, that was also norm x2 is also root 2. So we got correct option as B. Sorry, let V be C2 and standard inner product space, and alpha beta be two vectors in V, which the following are sesquilinear forms or is sesquilinear forms. This is incorrect because it doesn't follow linearity. Here is description for it. For B it is not sesquilinear, right? Because linear in first coordinate. Here is a description for B and C both. For C, this is description for C. C is this is f of alpha beta is equal to 2x1 square plus 2y2 square. You can take anything in y1 y2 beta, right? Basically y2, take any y2, different y2, and then now use linearity property. It will fail here, or basically because of these powers linearity fails in first coordinate. Okay, for this I think you have to give some counter example. A good counter example could be where I can write, for example, let's see for C we have f of alpha beta is equal to 2x1 square plus 2y2 square. Where alpha was x1 x2 and beta was y1 y2. Take alpha 1 is equal to 2 3, alpha 2 is equal to maybe 5 7, beta is equal to 0 0. Okay, so let's see in the first coordinate what is happening. So f of alpha 1 plus alpha 2 comma beta, this will become f of 2 5 7 10 comma 0 0 and this is 2 into 7 square means 98. If you calculate f of alpha 1 then beta plus f of alpha 2 then beta, we want to check if these are equal or not. Here we will get 2 3 0 0 plus f of 5 7 0 0. We are getting 2 into 2 square plus from the second 2 into 5 square, and now we are getting 8 plus 50 is equal to 58. So these two are not equal, as these two are not equal. So linearity in first coordinate fails because of these square terms, if you see. So similar thing is happening in part B also, right? There we have these terms x1 square plus y1 square minus 2 x1 y bar plus x2 y2. So here linearity in first coordinate as well as in second coordinate fails. In the second coordinate we need conjugate linear, and because y2 is not it should be y2 conjugate, it should be, and y1 conjugate it's right, but it should be y2 conjugate. But anyway, power of x is 2, it will become a good reason to fail being sesquilinear. Okay, like here we give counter example for this is for third C part, so give such a counter example for second also. Now parts D is correct because all these powers are singleton and there it will follow that this is sql uniform. Okay, verify it is easy to verify. Fifth question, sql uniform on R2 given by this. Matrix representation of f with respect to this basis will be, so this is your basis and you want to calculate matrix representation of f, then alpha ij will be given by this description. This is already discussed in the classroom and above also I mentioned it. It was needed to calculate it here. Here it is orthogonal basis or orthonormal, not orthogonal basis, but any basis will work as it was discussed in the classroom. I might be wrong, but orthogonal basis will in fact work. Okay, so we have orthogonal basis alpha I, alpha j. Now we can calculate matrix representation of f, and a11 will be calculated like this. Here alpha 1, this is also alpha 1, calculate it is 0. a12, similarly put these values in f is defined here, so you will get a12 is equal to 2, a21 is equal to also 2, and a22 will become 0. So you get the matrix 0 2 2 0, and option D is correct. Every else option is incorrect. So let's see next question. Given a linear operator T defined like this, on a standard inner product space C2, corresponding sesqui linear form will be given by. So you remember this was one-to-one correspondence between linear forms on V, and here we have linear operators on V. Finite dimension vector space, V is finite inner product space. Okay. Now if you remember this, now calculate fx like this. In the first coordinate t will apply, then inner product with second vector. This is how it is calculated. Now it was checked that option B is correct. Okay, look carefully and get for part 7, given an inner product space V which is R3, standard inner product on R3, linear operator is given by this, then the resolution of identity operator E1, E2, E3 is defined by. So let's see. First of all, we calculated characteristic polynomial for T, and we got 3 distinct eigenvalues. Now we'll get 3 distinct eigenvectors also, x1, x2, x3. Now check that x1, x2, x3 they are orthogonal also. Verify these things, calculate them, and note that x1, x2, x3 is orthogonal basis. Basis of eigenvectors. So T is in fact diagonalizable. Okay. Now what are 3 eigenspaces corresponding to, first will be spanned by x1, second will be spanned by x2, third will be spanned by x3. So projection in first eigenspace is given by this formula. This formula is also from this, also can be seen from Gram-Schmidt orthogonalization process. Okay, there also this formula is Smith orthogonalization process. So remember this formula. Given any random vector x, y, z, project in this direction. Project in this vector, unit vector, 1 minus 1 0 by norm 1 minus 1 0, and then multiply with this vector. This is becoming a constant now, and this is a vector. This belongs to F, field F, whatever C or R or general maybe, and this belongs to R3. So it is basically projection in this direction, 1 minus 1 0. So you get it. Similarly, E2 will be projection in second direction, and E3 will be projection in third direction, x3. So check all these values. So only option C is matching and all other are incorrect somewhere, some plus or minus mistakes. Okay, so this is how we calculated it. Now let's see for question 8. Given an inner product space R3, standard inner product space again, and I think T is also again the same. Now they are asking spectral resolution of T. So we want to write T in terms of C E1, E2, E3. So if you remember this spectral theorem, T also got such a decomposition, C1 E1 plus E2 E2 plus C3 E3, because we have three distinct eigenvalue. So we have three terms in the sum. Now C1 was 5, C2 was minus 5, C3 was 7. Now corresponding E1, put value of E1, E2, E3 you already calculated in the last question. Okay, so all this option is satisfied, option B. Everything else is incorrect. Somewhere there is some plus minus mistake in the values of E1, E2, E3. Okay, so verify it. Now question number 9. V be space of all polynomial over real field, and inner product is space defined by this integral. This is 0. Consider a function f on V, linear operator t on V. T is equal to f. T is just multiplication by f. Okay, t of something becomes f of that same thing. T star is adjoint of T. Which of the following statement is correct? For A, this is the discussion. We want to see if such a T star exists. This is defining property of T star. So we are having T f prime g prime is equal to this integration, because this is Tf, but Tf becomes f prime. This is just T f prime, so it becomes f prime into g prime dt. This is integration up to 0 to 1, but inside values f prime g prime, these are coming from these are basically polynomials, and polynomials are commutative, and there we have polynomials are basically groups. So there we have associativity, commutativity. Using all those relations, f can be taken with g prime and f prime on the left. So now look it carefully. By the definition, this is basically, this was nothing but f prime and f g prime inner product, but f g prime is again t g prime, right? That is what is written here, and this is matching with f prime. This is equal to, by defining property and uniqueness of T star is we got T only. So we have this conclusion here: T star exists and T star is equal to T. T star exists and it is self-adjoint. So option C is anyway correct and A is incorrect because C is correct. T star exists. Option B says T star exists and it's unitary. What unitary means is T star is equal to I. Nowhere it is given that T star is equal to I. For I, because this is polynomial space, right? Polynomial space, I means identity is 1. So when it is 1, T star is equal to 1. If and only if f and what t is f and T star is maybe T. What is T star? T star is again T. So T star becomes f square, multiplication by f square, and f square is 1 if and only if f is plus 1 or minus 1. So in case f is not plus 1 or minus 1, T star is not equal to identity. So it is not unitary. So this is explanation for B. What about option D? T star exists, yes, but it does not commute with T. It commutes with T because T star itself is T. So T commutes with T itself. Here is description. Okay, so T star exists and it is commuting with T. So option D is incorrect. Let's see last option. Consider a matrix M cross N, means M is equal to 2, N is equal to 3. Represented by U D V transpose. Okay, where U and V are orthogonal matrices of order 2 and 3 respectively. So here is this description. So total A was 2 cross 3 and U is 2 cross 2, V is 3 cross 3. So this would be of this form, 2 cross 3, and this diagonal in this square. Okay, and this extra column is 2n is the order of the product to be well defined. This product to be well defined. In that sense, I'm saying. Okay, so let's see how I calculated it. It was already discussed in the classroom how to do this, but let's see. Okay, so first we calculated A star A. So it was A star and this is A, and we calculated this was 3 cross 2, this is 2 cross 3, product becomes 3 cross 3. So calculated this product I had already calculated. Now characteristic polynomial of A star A. We got characteristic polynomial this and this. Non-zero characteristic values were 25, 9 and then 0. Okay, so these were lambda squares for matrix D. So now we see non-zero eigenvalues are here. For this A star A we have 25 and 9, but while writing D we see here that it will become square root of first eigenvalue, then square root of second eigenvalue. This is your diagonal part, and then extra zeros. This was your D. Okay, from here you get this. Why I am writing del square, lambda square, is discussed in the classroom, so you can check it. Okay, so once you calculated eigenvalues of A star A, you can get what D is. D is this. Now since okay, we also let that V is this x1 x2 x3, where x1 x2 x3 as column vectors, they are just eigen vectors of A star A. Okay, so for eigenvectors of A star A, we calculated for 0, for 25, and for 9. Let write them as lambda only, so don't be confused. Okay, so we are just taking square root of lambdas. Yeah. Now first of all, because A is normal, check it, A is normal, it is in fact self-adjoint, maybe it is self-adjoint or normal will self-adjoint will imply that these are all real eigenvalues. Okay, and they will be positive. They will be how positivity is decided. I don't know how positive. Basically, these all are. This is also not discussed in the classroom. In fact, their professor said these are all positive, and okay, I'm not going to do this. Basically, they are all positive, so we can take square roots. So whatever non-zero eigenvalues are, they will decide your diagonal part in the D matrix. So we calculated these eigenvectors x1, x2, x3 first, and then we calculated since we want V to be unitary, what? Orthogonal matrices. Orthogonal. These are all orthogonal vectors, but I'm just saying you that we can basically make V a unitary matrix. No, orthogonal. We want each column to be of norm 1, so that is why we will also divide x1 by norm x1 and update it. So this is how after dividing we get orthogonal matrix. We should say orthonormal matrix now, but anyway, it is orthogonal, that is for sure. So now we calculated A into V. A is this matrix, initial matrix, and this is we just calculated. Now we got this product as here it is. Now this is very easy to see it now. This is nothing but product of these two matrices. Okay, first write D here in the right side, and then you will find what U should be, this U. Okay, now it is easy. We found U also and V transpose also. So main thing to remember is we should go first for A star A and characteristic polynomial for A star A. Here we'll get eigenvalues which are basically lambda squares. While writing D, that will be helpful. Then calculate eigenvectors for A star A. Okay, and normalize them. You will get orthonormal set of vectors. Okay, so now your V is as a column vector. Each vector is just the eigenvector you just calculated above. Okay, for A star A. Now you have V, you have D, Now you just want to calculate u. Okay, so for that you write av is equal to something into d, and that something is coming by simple observation. Okay, and that is your u. Okay, so I end this session. This was just to discuss last uh, week 12 session where video recording was not successful. That was 2 hour session. I completed in 50 minutes. Please, all the best for your exams, and bye bye.